For example, in zip files, this is the last 32 kilobytes that you have coded. So it tries to predict whatever is going to come up from the last 32 kilobytes it has seen, and tries to find matches with those 32 kilobytes. And obviously, longer matches are better. If you find a match, several characters that match, for example, 2,000 of them, 2 kilobytes, you obviously can get a really, really big compression from that. But yeah, if the longest match you can find is something like 3 characters, depending on where in the window it is, it might be beneficial not to code it at all. So the longest match is not necessarily the best one. If you don't find any match with this history window with the last 32 kilobytes at all, then yeah, you just try to code it as is with whatever you used before. The result is a sequence of tokens, or so-called literals, which is just data that is stored literally, that is not changed in any way, and so-called match tokens, which are a reference to data that happened, say, 2 kilobytes before, 4 kilobytes before, whatever. And this compares to packet-based RLE schemes I mentioned earlier, because you have those packets of data that mark repetitions, and yeah, it's coded in a very similar way. Then you try to encode this token sequence. In plain LZ77, this is a fixed size code with a few bit fields that's used to code everything. Then there were further variants like LZSS, which has first a bit that tells, is this a match? So we have a reference and an offset in length here, or is this a plain character, in which case we just store the character. Or zip, which does some Huffman coding on top, and newer algorithms do arithmetic coding and even fancier methods and try to predict things, but it's basically always the same general idea with some processing afterwards. The take-home lesson on this, if you use something LZ-based, and you will, if you use an executable packer, you probably will have a packer that is based on the scheme, you want it to find long matches. So you want long string repetitions as is, that really just one string that appears multiple times. And if you manage to make data repetitive, so you have lots of repetitions, it's a good idea. And that's one of the reasons this kind of reordering is useful. Because if you have data that would match, say, every second character, you don't get any string matches at all. Because, yeah, it's just every second character, nothing continuous. So if you manage to make it be every character that matches in one part of the data and no matches at all in the second part, then you have a compression gain. And this is the main reason why you would do reordering on data. And the other part of this section is so-called context modeling techniques, which is a class of modeling techniques for arithmetic coding. As I told you at the end of part 1, in arithmetic coding, you don't need actual value counts. You just need probabilities. How likely is the next character going to be an A and B, whatever. And what you do is you predict the next symbol based on context. When context in this case means the last few characters you've read and the last few characters you have encoded, like last 2 or last 3. And then you collect statistics, how likely each character is going to happen in that context, and then build an overall prediction from that somehow. You usually have several contexts of several lengths and so on for a single character, and you have to mix that to get a good estimate of what character is likely to appear next. This somehow, how this is mixed and how this is calculated, is the main difference between algorithms, plus the details of how statistics are collected, because everyone has different data structures for that and so on. Some are more efficient, and some give better results than others, but yeah, it's really just a variation on the same theme. This type of coding has produced some of the best compressors you will see in the real world. I think by now the best general purpose data compression algorithm is PAC7 or PAC8, which is an algorithm that is based on this idea. But the drawback is you do a lot of work to predict individual characters. You have to look at different contexts, you have to calculate how probable each character is, you have to do arithmetic coding, so this is really, really slow. For example, a pack, like I just mentioned, is very good compression-wise, but it also compresses like about 9 kilobytes per second on a state-of-the-art machine, and it uses a few hundred megabytes of memory for that. So that's obviously a high price you have to pay there. So you can get very fancy with that, but it's not for free. And so the modeling details of how you would do that are rather technical, and it's not really interesting in the seminar. And as a user, I would recommend you treat it just like it is LZ with arithmetic coding, because it really benefits from the same kinds of things, like characters, long matches and stuff. This gives good compression in this kind of schemes too. And I only mention this because some next generation exapackers like Crinkler or a new experimental version of Crunchy I'm working on right now are based on ideas like this. So it may become important in the next few months or years. Which brings us to section 5, which is, basically most hands-on of all of those sections. And the first is about how to reorder data so you get good compression. The first one is about operator systems, so like our Farbrausch tools, where you have stacked operators. And the second one is about how I record a code to make it packbed, which is probably not of much interest to you as it is, but it shows some of the nicer things you can do in this reordering context. Okay, so on the operator graph tool, you've probably seen this kind of data structure, this kind of way of thinking, if you ever used a Farbrausch demo tool, or at least seen screenshots. And we have those blocks which are connected, in our case by stacking, or some use arrows like in Buzz. Data is moved from one point to the other and that kind of thing. And other tools that are not this explicit about the way they do it still use a similar representation of operations arranged in a tree internally, even though the user doesn't really see it. So this is probably the way most intro tools work internally. And successive operations on the data you do are stored together with the parameters. This by itself is nothing spectacular. Every application that has any kind of undo functionality has to do that too. So it can revert operation, it needs to know what exactly has been done and have a reverse step. But in our case, and that's the interesting part, the history is not a linear list of operations, but a tree. So you can make branches. You can use the same source for two different destinations. You can have links between the things. And this is really a lot more flexible. And more precisely, it's not really a tree, but a so-called DAG, a directed acyclic graph, which basically looks like a tree, but also allows you to have a limited way of relationships that are not really tree-like. So you can have pointers upwards too. This operation history of what has to be done to reproduce the intro data that the graphician did is then stored in the intro. So we're interested in how to make that pack well, because that is the main part of data we would store in any intro. Well, first, this is basically a tree, or looks like a tree at least. So you can do standard techniques you would do in trees. When you have a tree, you can do something called post-order traversal, which basically means you just recurse down into the tree, and by the point you're out of recursion and you're returning back, you write which node you're currently on. For example, this is a color correction operation. And when you know how many inputs each operation gets, that's all you need to know. You just need this operation, and by the way things are stored, you automatically generate everything in the right direction. So you do this post-order traversal and write out operator type IDs that just tell you what kind of operation is happening now, color correction or generate a cube, that kind of thing. And you write it out as you go, and that, together with the parameters for the operation, is all the representation you need. It's not technically a tree, but a DAG, so you can have this